All right, today is the 10th, and we are going to look at mathematical induction. Mathematical induction is an interesting word. Induction, as I've said before, is all about seeking patterns in things. Deduction is the more formal proof. This is sort of the bizarre child of both. If you have an idea or an observation that seems to be true about numbers in particular, mathematical induction can tell you if it's really true forever. Because in math, nothing is mostly true. It's either true always. You can find one counterexample, it's false. Some people find that more comforting than other areas of life, but sometimes it can also be scary. So mathematical induction is about proving things are always true out to infinity, and it rests on a couple of assumptions. There's really a two-step process. Well, I'm going to call it a three-step process here. You can describe it a couple of different ways, but given a hypothesis, and your hypothesis will be a mathematical statement. 1. Prove it is true for n equals 1. Now, we've been studying sequences and series, and this is the same n equals 1 that's a counter for sequences and series, because if you're trying to prove a mathematical statement is true, you want to prove it's true once, twice, 3, 4, 5, some integer number of times up to infinity. So prove that this, whatever you're talking about, is true when n is 1. 2. Assume, which is a fun word to write in a math class, but it's actually appropriate here. Assume it's true for the kth case, which makes me sound like I'm speaking with a lisp. Assume it's true for the kth case. What does the kth case mean? K is just some number. Try and say kth case 5 times fast and see what happens. So you assume it's true for some numbered case, whatever rule you're talking about. 3, prove it's true between, which I suddenly can't spell, the kth and k plus 1th case. There's 2 assumptions here. One is that whatever rule you're talking about will work like a ladder, actually 2 analogies, a ladder or a set of dominoes. If it works like a ladder, the idea is if it's true from this rung to this rung, for any numbers, it will be true for all the rungs up to infinity. And the other assumption is if you think of a mathematical rule as being like dominoes, as you add numbers to this rule, as you go down up towards infinity, down or up towards infinity, depending, if it knocks over dominoes 5 and 6, it'll knock over dominoes 6 and 7, it'll knock over dominoes 7 and 8, and onwards. But you don't have to prove that any 2 dominoes will fall. There's one way to look at this analogy.
So that's like, if you can divide a number by 2 and 3, you can also divide it by 6.
A little bit, yeah, a little bit. And then that's true for any multiple of 6.
Right.
In a few minutes, you'd be able to see, that's an observation that sure seems to be true. By the end of this class, you should be able to prove that that really is true for all numbers up to infinity. Because right now, you don't know that. I'm assuming you haven't tried it for every number up to infinity. Not even sure. Wouldn't be here right now, and you'd starve to death. I'm going to leave these rules up for a minute. So Tyler, can you follow me over to this board so I can point back to those rules as I do an example? And I am totally taking the examples from the book. I am not making this up. A while back, I told you about a 10-year-old boy named Carl Friedrich Gauss who figured out a super quick way to add up all the numbers from 1 to 100. And his way led to a general rule that now I'm going to treat as a hypothesis, even though I know it's true. Treat it as a hypothesis. The sum of the first n integers is n over 2 whoops, I was about to give you the rule for the arithmetic sum. It's the same result, but this is phrased differently. So it is actually n times n plus 1 over 2. So in little Carl's case, he was adding up 1 to 100, right? So if I rearrange this a little bit, for example, if you're adding 1 to the sum of the first 100 integers, 1 plus 2 plus 3 plus 4 up to 100, 100 over 2, and then I could write this as 1 plus 100. This is my 1 plus n. This is our n over 2 a sub 1 plus a sub n rule, right? Well, if all you're talking about is integers, this rule breaks down even simpler. If all you're doing is adding 1 plus 2 plus 3 plus 4. This is for any arithmetic series. And so we've talked about that example before. How do we know this pattern will always, always, always work all the way up to infinity? For any integer you can choose.
Put infinity for the a sub n. That doesn't work.
Gets you infinity. It's a little bit, doesn't work as well. So we're going to follow those 3 steps over there. We're going to prove it works for 1. So first thing, does it work if n equals 1? Well, let's see. Then I put in 1 times 1 plus 1 over 2 is 1 times 2 over 2, which is 1. What should the sum of the first 1 integer be? 1. Okay. Now be careful with this. There's a danger.
Is that always true?
That's a good question. There's a danger to using this as a first example. Okay?
Because 1 is like a weird number. Like it's not a good number.
Well, yeah, the question is, does it work for n equals 1? But the answer doesn't have to be 1. If I was using a different rule, I could get a different answer. And I'll show you that in a sec.
How would it not work?
Any number?
Well, how could this have not worked? Let's say if I put in 1 and I'd gotten 3. Then I would have said, okay, this rule doesn't even give me the right answer for just adding 1 integer to nothing.
Okay.
But 1 doesn't have to be your answer. That's the only reason I said it's a bad example, because for a different rule, this answer would be different, but the number we're testing is the number 1. But this is still a good starting point. Okay, 2. I assume it's true for the kth case. In other words, I'm going to assume that the sum of the first k positive integers is that number k times k plus 1 over 2. Okay?
So you've kind of just switched the variable.
Just switch n, the general counter, to k, some specific number. More specific. Perfect. Well said. Now 3 is assuming it's just true for that number k. I don't even care what k is. Now we have to prove it's true between the k and the k plus 1 kth. In this case, and this is where there's a different sort of trick for each type. And sometimes you got to get creative with this. For summation rules, it's pretty simple. What we have to do is we have to take the sum for k integers, and then we'd want to add the next integer to that. So if this were 50, I would want to add 51 to that. That should get me the same thing as if I plugged in k plus 1 into the rule.
Yeah.
Does that make any sense?
Yes. That makes a lot of sense.
So the sum of the first 50 terms plus 51 should be the same as if I put 51 into the rule. The sum of the first 127 terms plus 128 should be the same as if I plugged 128 into this rule. Now, how am I going to prove that this is always true no matter what two numbers, k and k plus 1, might happen to be? Well, if I can algebraically prove that this is always true...
Wait, is it k inside the...
That's a k plus 1 inside these parentheses. I put k plus... Everywhere there's a k here, this k and this k, I put k plus 1 in on the right side of my equation.
Okay.
Now,
where's the plus 1 from?
well, if this is 50, that's 51. If this is 2, that's 3. If this is 11, that's 12. Whatever number this is, I have to add one more than that number on this side, and I have to put that in my formula. The 50th plus the sum of the first 50 terms plus the 51st term has to equal whatever I would get if I just put 51 into the formula.
I don't understand why there's a k plus 1
Plus 1?
Why shouldn't there be a k times...
What would happen if I,
Why isn't that there?
let's go back to this one a second. This is the sum of the first k terms, right?
Wait, you skipped a...
Because k plus 1 is n.
I'm
Yeah.
just...
Okay? So let's follow me here for a sec, Noah. Take a look at this. If I just write s sub k plus 1 here, that means put k plus 1 into this equation anywhere there's a k. So I'm going to take this k, write this one right here, and I'm going to replace it with k plus 1. I'm going to take this k, and I'm going to replace it with k plus 1, but there's already a plus 1 in there. The 2 doesn't get changed. No, it's good for me to break down that step.
Oh yeah, I was wondering, but how does s sub k plus k plus 1... So
Equal that?
is that telling you that for every place there's a k, you put in k plus 1?
Nope, this is telling me that if I were to add up the first 9 terms of this,
Yeah.
and then I were to add the 10th term, because if k is 9, k plus 1 would be 10.
Wait, wouldn't it be
But that would be the same.
S,
Yeah.
S sub k plus a sub k plus 1?
Yes, but in this case I'm in luck because we're adding up all the integers, so it's the same thing.
Oh.
So if this is the sum of the first 9 integers, this will actually be 10.
This is-
But in general, for an arithmetic sequence, yes, that would be a sub k plus 1. Very good, Joey. Daryl, you have a question?
I wouldn't say, wouldn't you just keep k for k and then just add the k plus 1 at the end?
So why don't you mean just why not write it like this? K times k plus 1
And then k.
over 2 plus
Yeah.
Yeah.
k plus 1 equals, that was going to be my very next step.
Yeah.
Yeah, so...
Can I go ahead and make this k plus 2 now?
Yeah. Okay, now it's like.
Okay? Now, if I can algebraically prove this statement is true without plugging in a number for k, then I've proven that it's going to be true for any consecutive integers. In other words, I'm going to prove that one domino will knock down the next domino no matter what numbered dominoes those are, whether they're 5th or 6th or whether they're the millionth and the millionth and 1. Does that make sense as an idea? I just have to prove that any 2 consecutive dominoes will fall, or another way to think of it is I just have to prove that from any rung you can reach the next rung on this ladder. And if you prove that's true without using a specific number, then you know it will work forever. And that's mathematical induction in a nutshell. To prove this is true.
Mr.
Wait.
Is
Yeah.
this an arithmetic?
This is an arithmetic series. Yeah. So I've already given you the rule and told you that it works, but I didn't prove it.
Yeah.
I said, hey
we're
kids.
gonna-
So now, I'm going to decide, I decided if I'm going to prove this is true by making a common denominator between these two. I'm going to try and algebraically get these to look the same. Everybody good with where I am on this one?
Oh, I guess.
Okay. So I'm going to make this now k times k plus 1 over 2 plus 2 times k plus 1 over 2, and that still equals k plus 1 times k plus 2 over 2.
Wait, I have a question about the one before that.
Yes.
Actually. So how are you, if you put those two together, how is that k plus 1, k plus 2 over 2?
I can't wait to find out.
Oh,
I should actually, at this point, I should actually be writing a question mark over it, Jen.
He's trying to.
Because
So you're trying to
that's what I'm trying to prove, yeah. Because if I can't prove it's true, or if I get a false statement, then this rule does not work all the way to infinity, no matter how many times it seems to work if you test it.
Yay, we're back to this.
Yay! Alright, so now that I've made a common denominator, my new numerator is k times k plus 1 plus 2 times k plus 1 over 2. Still equal to the same thing, still a question mark. And with a little bit of distribution, this is going to become k squared plus k, and then I'm going to add this k to 2k, so that's plus 3k plus 1 over 2 is equal to k plus 1 times k plus 2 over 2. What would I get if I FOILed these two?
You would
You
get
get
k
k
squared.
K squared plus 3k plus 2.
I hope plus 1, Tyler.
Oh.
Hello, that's a problem.
Yeah.
I love it when this, ha ha ha. Guys, when you distribute a 2,
Oh.
Yeah.
That's awkward.
wow, okay. To apologize to anyone watching this, not in this class, on the internet right now, but yes. So, Tyler, you were correct. K squared plus 3k plus 2, which is what we should have had over here. We came this close to failing to prove that something worked to infinity when actually it does. So for an arithmetic summation, for an arithmetic sequences summation formula, this is actually the consistent thing you do. In fact, you can write a general form for that. You can take a moment, let you get this down. Meanwhile, Tyler, follow me over here a sec. If you're trying to prove the sum of an arithmetic series, you'll always test for 1, and then as Joey observed, you'll always be trying to prove the sum of the first k term plus the general k plus 1 term is equal to the sum of the k plus 1. You'll test it for 1, and then you can jump right to this algebraic statement. You have to plug in a different thing for each rule. If I have time, I'll go back and do another example of that, but there's a more difficult example of mathematical induction I want to go over first to make sure I at least touch on both types that we're going to talk about today. Any questions on what this means, though? For any arithmetic series, the sum of the first 12 terms plus the 13th term should equal the sum of the first 13 terms.
Wait, can you repeat that again? Sorry.
The sum of the first, pick a number, Jen.
8.
The sum of the first 8 terms plus the 9th term should equal the sum of the first 9 terms. Does that make sense? The sum, there's 6 of you in this class, the sum of 5 of your weights plus the 6th weight should equal the sum of all 6 of your weights, right?
Yeah.
Okay, this is a really general way to write that idea. And for any arithmetic series, what you'll do is you'll just test for 1 and jump right to proving this. Problem is, what if it's not an arithmetic series? Then you have to get really creative. The 2 things we're going to talk about today are arithmetic series, that's one example, I'll do another if I have time, and the other is divisibility rules. Divisibility rules are a little trickier and you have to get creative with the algebra, so I'll show you 2 creative tricks. But mathematical induction can be done for any rule you can think of. It just, they get weirder as you go. Can anyone think of what numerical rule people have been looking for 3,000 years or so and still haven't found or proven a rule for?
Pi?
No, pi's pretty well figured out actually. We got and then you know those infinite series I gave you for sine, cosine, and e the other day? There's a couple of those for pi actually. But pi's well thought out, e's well thought out. It's actually simpler than that. And you learned about it before you learned about pi.
Gravity?
Not really new, not abstract enough.
No.
But yeah, gravity we're still trying to figure out too. Prime numbers. We don't have a consistent way to predict prime numbers out to infinity, and the first person who comes up with it will have an unbreakable code at the very least until somebody else figures it out. It's actually a fun little conspiracy theory that the NSA has proven what's called Riemann's zeta function and uses it for codes and won't let any mathematicians know about it because other people could break it then. That'd be funny if it were true. But more simpler than that. I have a hypothesis.
It'd be horrifying if it was true.
Dan Brown, call your agent. Next book coming out. Here's my hypothesis. That if I raise 4 to any integer power and subtract 1.
Wait, is this an example?
New example, thank you, yes.
Okay.
If I raise 4 to any integer power and subtract 1, it will always be divisible by 3. It's a pretty random little rule. 4 to any power minus 1, I will always get something divisible by 3. Running through it in my head, I will say it is true for 1, 2, and 3. Beyond that, I think it's worth checking it out. So what's the first thing you always do with mathematical induction, which is easy to forget?
Prove it.
Prove it for what?
Prove it's true for n equals 1.
Yep, Tyler, follow me over here now. Yep, easy rule to forget, okay? So, 1, we test n equals 1. What's 4 to the first power minus 1 equal?
3.
Is 3 divisible by 3?
Yes.
Yes, it is.
Check, check. Move on to step 2. Okay, now, step 2 we sort of brushed through on arithmetic series because it's not really necessary, but for this one it is. I'm going to assume that 4 to the n minus 1 equals 3 times r. The only thing I need to know is that r is an integer. The only thing I need to know is that r is an integer. So I'm just going to assume it's,
Is there a symbol for that, or you just ran away?
not that I know of actually, yeah, it's just, I don't know, I don't know, there's no, I mean, and actually I'm sorry, for 2, I'm going to make this k, not n, my apologies, that should be k. A couple things are used pretty consistently. N is generally used in situations where you want to stick with integers, so is I, when you're not talking, as long as you're sure you're not talking about the square root of -1. K is often used when you want to talk about a constant, but none of those are like hard and fast rules. You can use n to equal a decimal variable if you want. But in general, if you see an n, they're usually saying I want that to be an integer. Here we're using r. I don't know why. I'm going with the same as your textbook for those of you who will double check it later. Okay, now, here's where this gets tricky. I have to demonstrate that if this is true, if my assumption is true, it will remain true as I jump from k to k plus 1. I know it works for 1. I'm going to assume it works for any other integer I put there. If I can prove then that it works from any integer to whatever integer comes after that, then I know that I can start at 1 and go up to infinity, and the next rung on the ladder will always be where I expect it to be, or the next domino will fall. If it works for 1, assume it works for any integer and prove it works for the integer after that, then you know if you start at 1 and keep going, all the dominoes will fall. So what I need to do is algebraically manipulate this so that I get 4, here's my goal. The goal,
Should you make it 3 then?
well, we're on step 3.
We are.
The goal of step 3 is to get 4 to the k plus 1 minus 1 equal to 3 times any integer. And to know that's true. That's the statement we need to get. The most important part is that we change this k to a k plus 1. Now this is an exponent with 4 as its base. How can I increase the value of an exponent with 4 as its base?
Multiply it by 4.
Multiply it by 4. Multiply it by 4, I'll add 1 to k. If I multiply it by 16, that would be k plus 2. Multiply it by 64, that would be k plus 3.
Wait, I have a
But
question.
doesn't that multiply 3?
Well, then I got to multiply everything by 4.
Yeah.
So hold that thought a sec. Yes?
Why are you getting 4 to the k plus 1? Like, why are you
Because-
doing...
This is my goal is to show that if this rule is true, it
so-
has to also be true for the next k after it.
So you're just putting the k plus 1.
Yep, I'm just putting it there. Now this is my goal. Now I have to algebraically figure out how to get from here to here and see what else happens. Joey just said I can take 4 to the k and make it 4 to the k plus 1 by multiplying by 4. And he's correct. But then I have to multiply everything on both sides by 4 and just see what happens. And see if I can change whatever I get to this.
Wait, so you no longer need the plus 1 because you multiply
Well,
by
it's the same thing.
I'm not, well, okay, this is my goal. Now I'm going back to this statement
and
and
go-
seeing if I can change it into this.
Okay.
Now this is going to get me 4 to the k plus 1 minus 4 equals 12 times r. But do I want 4 to the k plus 1 minus 4?
But you didn't, why did you distribute
Not
the 4
really.
to the first one?
I did. That's where this plus 1 came from.
'Cause when you
This is 4 to the first. Multiply two numbers of the same base with exponents, you add the exponent. That's what I'm going to get from 4 to the k to 4 to the k plus 1.
But isn't 1 plus 0 just be, or 1 plus 1 be 2?
Well, these aren't different bases. These aren't the same bases. This is just 4 times 1. Is that what you're referring to?
Wait, 4 times k.
If it was 4k minus.
Yeah.
Oh,
4r.
I see what you're doing, okay.
Here I'm just multiplying 4 times 1. Here I'm just treating this as a to the m times a to the n, and I'm adding the exponents. Now, my goal is not to prove anything about 4 to the k plus 1 minus 4. My goal is to prove something about 4 to the k plus 1 minus 1. But 4 to the k plus 1 minus 1,
Well, if you divide by.
I'm not going to divide. That's a good idea. That's a clever idea, but I think it'll be easier to just break up. Can I just take minus 4 and rewrite it as minus 1 minus 3? Is that allowed?
Yeah.
See, if I divide, unfortunately, Michelle, I would get rid of this k plus 1 as well. That'd be problematic. So this will then become 4 to the k plus 1 minus 1 now equals 12r plus 3. This side looks like my goal. But what I have to prove is, remember, the whole goal is to prove that whatever you do when you raise 4 to any power and take away 1, you always get something divisible by 3.
Take out 3 from that side. Oh, wait, then
And what's left? No, you're good. That's brilliant.
Then
Go,
it's
go, go.
4r.
4r
Plus 1.
plus 1.
Oh.
Excellent. Now, follow me here, Kiddlywinks, because believe it or not, we're done and you might not notice it. If r is an integer, if you multiply 4 times an integer, do you get an integer? If you add 1 to that integer, do you still have an integer? Yeah. Okay, so what we've discovered is 4 to the k plus 1 minus 1 will always equal triple some integer. And if this is...
That's what that is over there.
Yep, and if this whole number can be broken down to 3 times something, then this whole number is divisible by 3, right?
Wait, can you say
Oh,
that again?
yeah.
Wait,
Okay.
So,
If you can take a number, take any number you can imagine. Okay, take this and take any number you can imagine, m. If you can factor it into 3 times some other number, then this number was divisible by 3, right? That was our whole goal to prove. You assume
okay.
that 4 to the k minus 1 is 3 times some integer. And then if you can assume that and then prove that 4 to the k plus 1 minus 1 is 3 times another integer, then you know that this is always divisible by 3. It works for 1, you pretend it works for some other number, and then you prove it works between that number and the next one. And you've proven it'll work forever. No matter, because we didn't pick any specific number.
Very smart.
These are tricky. Pardon?
Very smart.
Yeah.
Wait, so like on a question, would it give us that, and then we have to like?
Yep.
is it-
Prove 4 to the n minus 1 will always be divisible. Did I write divisibly? Will always be divisible by 3. And we've done that. But coming up with these algebra tricks can be hard. It takes practice to recognize them. I'm going to do one more divisibility rule that has a different trick in it.
Wait,
See,
I
that's
have
a-
a question,
yeah.
sorry.
Please.
For the very beginning of 3,
Mm-hmm.
when on the right side, when you got 4 times 3r, what made you come up with that number?
Here.
There. Yeah, what made you come up with
Okay.
the 3r?
I needed to, well this, step number 2 was assume that 4 to any number minus 1 really is divisible by 3. And my way of writing divisible by 3 was saying it can be represented as 3 times some other number,
Okay.
some other integer. So this is just an algebraic way of saying this is a number divisible by 3.
Okay.
Here I multiplied both sides by 4 in order to get this k to be a 4 to the k plus 1. And if I multiply this side by 4,
You have to do it to both
both sides, yep.
Okay.
Whatever you do to one side, you have to do to both.
Yeah, but I thought you were just like taking it out, like.
Oh no, this isn't factoring, this is multiplying. Bless you. Here, I wasn't factoring out of my goal. I was multiplying both sides by 4, both sides of my assumption from number 2.
But you got rid of the plus 1 there.
Oh no, this, here was my goal, right? This is not the step afterwards. These aren't related directly. I should have written this part again, sorry about that. This 4k minus 1 equals 3r is just from my step 2. And then I jumped right to multiplying both sides by 4. But sorry, no, this is not...
How did you know that I'm going to start with these numbers?
How did I know I was going to start with this?
No, like with what you put below the goal.
Below the goal?
Yeah, how did you know you were...
Okay. Let me redo these steps real quick. This is good. This is good. Okay. Here was my assumption. Okay. Here's my goal, is to prove that if I just add 1 to this exponent, I'm still going to get 3 times some integer. Okay? Once you know what your goal is here, what I should have done, you rewrite your assumption from step 2. And you rewrite it correctly. Okay? You rewrite your assumption from step 2. And then you look at your assumption and say, how can I get to my goal? Well, the only way you're going to get from 4 raised to a k to 4 raised to a k plus 1 is to multiply 4 to the k times 4. But you can't multiply one thing. Back to algebra 1 now. You can't multiply one thing by 4. You have to multiply everything by 4. Both sides and each term.
Can we start on the new example?
Yep. So this is going to be 4 to the k plus 1 minus 4 equals 12r, and I didn't show this step clearly. But what you do first is you rewrite step 2, and then you have to ask yourself, how can I get from step 2 to my goal? And that's where the multiplying by 4 came in, and that's where the creativity comes in. That's where there is no one formula for this. But no, thank you for asking me to rewrite that, because that's clearer, I hope. All right, Tyler, follow me back here for the next example. There's a trick on this one that is crazy. You are you're going to wonder where I got it from. Actually, it's an example in the book, but I didn't like the way the book did it, so I came up with a slightly different trick. Okay. New example. Prove that 6 to the n minus 2 to the n is divisible by 4 for all integers n.
So step 1, we just needed to...
Step 1.
6
To the first.
minus 2.
Equals 4, okay.
Okay, is 4 divisible by 4?
I hope so.
I think we can roll with that one. We'll take that one on faith. 2.
Why did you say n equals 1 is dangerous?
Oh, it's easy to forget. Oh, on that first example?
Yeah.
You remember you're just testing, thank you for reminding me of that. You're just testing that when you put n equal to 1, but your answer doesn't have to be 1. In fact, in this case, our answer had to be 4 or 8 or 12 to go on. Because in my first example, I had n equals 1, and I got an answer of 1. So I didn't want you to think that the answer was the important part. Does that make sense? Now we write our assumption down. And our assumption is that no matter what n is,
Is it K?
no matter what k is,
Would it be
shall I have you double check everything I do for the rest of my life?
6 to the k minus 2 to the k equals 4r?
No, 6K.
Perfect.
2K. Yeah.
Yeah, 6 to the k minus 2 to the k will equal 4r if we follow the pattern of the last one. Very good. Divisibility rules do have a bit of a pattern to them. Now, for 3, here's our goal. 6 to the k plus 1 minus 2 to the k plus 1 equals 4 times some other integer. Will not be the same r from last time. We just have to know that whatever's left after we get a 4 on that side is an integer.
Why do you add the 1 to it?
Because we're proving that, we're assuming it's true for, pick a number, any number.
3.
We're assuming it's true for when k is 3. Then we're checking to see if it's true when k is 4.
Okay.
But we can't use 3 and 4 because that's still a finite check. That's still just a regular inductive check. Sure seems to be true for the first 100
So
numbers
you always
we pick.
do that, you just add the 1 to it for
Yep.
step 3.
Yep. But it's a little different between divisibility rules and proving a summation series. So you can't forget that other formula I wrote. And if you try to test some other mathematical idea, you have to come up with a new way to phrase your goal. But we're going to stick to these two for now. I'm just sort of letting you know that this exists and that these rules we give you, we don't just make them up or check them for the first 50 numbers and figure they're true. People actually know that every one of these rules I've given you about numbers works to infinity. And that's how you know, without actually spending an infinite amount of time checking it. Okay, so I need an algebraic way to turn this into this. Now it's fair. Well, hold on one sec. I want to say one thing before we go. Multiplying this by 6 will get me 6 to the k plus 1. Multiplying this by 2 will get me 2 to the k plus 1. But it has to look exactly like this. It can't change to plus. I can't have a coefficient there. So that's the tricky part. Okay? But there is something kind of magical you can do. Are you ready for this one?
Okay.
Who remembers the idea of the complex conjugate from imaginary numbers?
Sure.
It was based in the difference of squares rule.
Cricket.
Okay. This is a little bit like this. Thank you, Tyler. So here's what I'm going to do. I'm going to take 6k minus 2k equals 4. I'm going to rewrite my assumption. I am going to multiply both sides by 6 plus 2, not 6 to the k plus 2. Now, multiplying, what's another way to say 6 plus 2?
8.
That's what
Wait, that was it, right?
Yes. No, I hesitated because I may have done this
Yes.
slightly wrong. That was bad body language. I was thinking about something else, actually. This won't change my answer, but I actually think I did this wrong on my little scratch paper over there. Okay, so there's something else. Anyway, here I have to FOIL. And I'm not just going to get 6 to the k plus 1 minus 2 to the k plus 1. I'm going to get something else. But I had to pick 6 plus 2 because I needed to get 6 times 6 to the k to get me 6 to the k plus 1. My outer will get me minus 6 times 2 to the k. My inner will get me plus 2 times 6 to the k. And my last will get me minus 2 to the k plus 1. Then I'll have 32r over here. Now, I've got the two terms I want. I needed 6 to the k plus 1 for my goal, minus 2 to the k plus 1. I've got those, but I've also got some extra things that cannot be on this side of the equation.
extra.
Wait, will that cancel?
Well, can't you just
No, they can't cancel because
can't you just bring it over?
Oh, right.
I can bring it over. 6 to the k plus 1 minus 2 to the k plus 1,
Equals
32r, plus,
6 times 2 to the k.
Yep.
Minus 2 times 6 to the k.
thank you. Okay? Boom. I've got my algebraic statement for the next term after 6 raised to the k power minus 2 raised to the k power. Is this definitely divisible by 4? Is my question now.
Yeah.
We don't know.
Wait,
Can we find
sorry.
out?
Okay.
Please, yes.
I get how you get for the right side of that. Like, what? I don't get how you did it.
Okay, you get how I
No,
foiled
no,
these.
down. Yeah.
Down?
Yeah, and I get that, but what I don't get what you put on the right side of that.
Okay, I took these two terms
Yeah.
and just moved them over to here. The reason why is because I needed to just have the 6 to the k plus 1 and the minus 2 to the k plus 1. Then it really is the next step in the sequence.
Wait, it is.
Hold that thought. Wait. No, go ahead and say it, actually, that'll work. Go ahead.
It doesn't matter if it's messy.
Because
It's still an integer.
because 2 is a factor of 6, so if it's wait, no.
Can you
Which is
rewrite
a
it?
factor of 4.
32 are.
'Cause-
Wait. Does it?
So 6 could be 2 times 3, and then if you're multiplying that by 2, then that by at least
Well,
1,
it-
2, so then
You're right, but there's an easier way to say it. There's an easier way to write
It's
it.
just 2 to the k minus 2, and then
Oh, so close.
Wait, 2 to the k minus
Can 2 to the k be rewritten
6
As
to the k
2
minus 1.
times 2 to the k minus
Right.
1?
Exactly, that's what
I
I
know
was
Joey was circling in on that, like a
Yeah, that's what
blind shark
Wait,
looking
I
for
had-
minnow, but
how,
it's,
wait, how do you do that?
well,
because, yeah,
Doesn't that just make it more complicated?
you're just.
oh, but hold that, but it gets us there. If I have 5 to the 7th power, is there any reason I can't rewrite that as 5 times 5 to the 6th?
You can.
You can.
Yeah, but
Or
that's
5 to the
easier
5
to
times
understand.
7 minus 1?
Yeah.
Yep, we gotta prove something here. Damn it, Jen, we have to prove something, not understand it. Sorry, that was wrong, but that's what I first thought of. Now I can change 2 times, ideally we're going for both, Jen, proving it and understanding it, I apologize for that. I'm going to change 6 to the k now to 2 times 6,
Times 6 k
Times 6 to the
minus
k
1.
minus 1.
okay? And now I get 32r plus 12 times 2 to the k minus 1 minus 12 times 6 to the k minus 1. My coefficients are 32, 12, and 12. Can I factor a 4 out of all of those?
Yeah.
Now, that's 4 times 8r plus 3 times 2 to the k minus 1 minus 3 times 6 to the k minus 1. R was an integer. If I multiply 8 times r, will I still get an integer? Everybody confident with that? 2, okay, well this k, we started out by testing 1. So k is going to at least be 2. If not 3, 4, 5, 6, 7, 9, 27, 52, who cares? If k is an integer, and you take 1 away from that, will you get an integer? Yes? And if you raise 2 to any integer power, will you still have an integer?
Yeah.
Okay, so 3 times 2 to any integer will be an integer, triple it, you still have an integer. Similarly, 6 raised to any power,
Wait, we assume k is above 0, right?
well, we started at 1, and I didn't say this clearly, I should have, thank you. We started by testing 1, and now we're assuming k is 2 or higher.
Would it have mattered? Couldn't you just?
Yeah, well, no, because negative exponents, we lose integers.
Wait, so I didn't know if you factor something out, you can just leave the ones there that you can't put things in, put the thing you factor out into?
Yes.
Like the 2 and the 6?
Yep. Yep, you can't combine these at all, can't do anything with it. But I know that k is 2 or higher, I know that k is an integer. That's sort of the whole basis of this, but I don't think I said it
When you
clearly.
first have it over at 32r plus 6 times 2,
Mm-hmm.
k. No,
K minus 1.
1 higher.
Yep.
That couldn't you just divide everything by 4 and then just leave it ugly?
No, because then you don't, the thing is, none of this matters, Noah, unless we know for certain that this is an integer. If this is not an integer, then this result is not evenly divisible by 4, and then our rule falls apart.
Okay.
So you have to absolutely know for sure that what you're looking at in parentheses here is an integer. That's why I'm going through this last step of saying, okay, assume k is an integer 2 or higher, then you'll be raising 6 to an integer power, you'll be raising 2 to an integer power, 3 times any integer will still be an integer, 3 times any other integer will still be an integer, and if I add 3 integers, I will still get 4 times some integer. So this rule is always divisible by 4. We can now say, with confidence, that 6 to the n minus 2 to the n will always equal 4 times an integer.
K plus 1.
Well, now we can say it for n, because it worked for k, And we were able to make the jump from k to k plus 1 and still get an answer that was divisible by 4. So now we can go back and say it for n. Any integer you could imagine, positive, starting at 1. Since we started at 1, this rule only works for 1, that we know of. Maybe it works for other things, but we don't know that, we haven't proven it.
How does all this stuff equal 4 times an integer? Like, what are you?
Remember, this was our assumption.
No, yeah, I mean for that, like how are you like, oh, we'll do this and this, and that equals 4 times an like.
Well, it was 4 times everything in parentheses, right?
Yeah.
So all I have to do is be sure that whatever in these parentheses will be a whole number.
How do you know that?
Well, k is a whole number at least 2, because we started at 1. So if 6 is raised to any whole number.
So we know that k is a whole number. So
Yeah.
Then it'll be a whole number.
So if k is a whole number, k minus 1 is a whole number, 6 raised to the k is a whole number, triple that, you still have a whole number.
Okay.
Same thing here, 8 times a whole number is a whole number. Add 3 whole numbers, you'll still get a whole number.
Okay.
Alright?
So if we have a fraction in our thing, then we know we did something wrong. Or it's
Bingo.
not true. Okay.
Yep. I believe the ones I'm giving you tonight are all true. So keep going till you prove it.
What if the
That can be
fractions-
frustrating to know.
What if fractions add up to a whole number?
Yeah, that can be hard to prove. We're not gonna. I think the ones I give you tonight, I didn't run into any of that. But if you wind up with a fraction, but you can prove that, like, I mean, some of them can be deceptive. Like if you get 2 to the n or 2 to the, let's say you get 2 to the k plus 1 over 2. That can be confusing until you remember that that's always just going to be 2 to the k. So some of them are a little trickier. If you got like 6 to the k over 3, well, that's 2 to the k times 3 to the k, right? So that is 2 to the k times 3 to the k minus 1. So sometimes you could wind up with a fraction. In general, you could get creative and trip over something like this tonight. So sometimes you could get a fraction and you don't know, hey, that actually will always be.
Are we gonna review this tomorrow?
Yes, nothing to do tomorrow. Okay, Tyler, go ahead and kill it.
Wait.